Okay, thanks for attending this small workshop. And I hope that all of you already have some ideas about what is KZG backend proving systems, and you know there's rumors or maybe benchmarks around there say that actually most of the KZG backend circuit are written in Circum, Halo 2, or something else that runs pretty slow in CPU, right? And today I'm going to introduce our way to somehow improve the performance, but not in CPU, but in a relatively expensive hardware called GPU 4090 to somehow bring the benchmark, bring the performance back to a level so that it can compete with some other proving systems. So the agenda that I'm going to give today is I'm going to quickly go through what we are building and then give you a map about the benchmarks between CPU and the GPU and tell you about what makes so difference of optimization in GPU and how we do that. And I will show a little bit about our progress on somehow bring about 30 to 50 proof speed increase on transplanted KZG backend from CPU completely into GPU. Okay, so let's start with our VM. So we are writing WebAssembly zkVM. That is, zkVM actually supports WebAssembly execution and generate proof for the execution. And so presumably you all know what WebAssembly is, and I give two supplementary on what WASM is that WASM natively supports host applications, and WASM is extendable with SIMD, which are vector instructions. And the way that we handle the WebAssembly execution is that we do a slice splitting of the full execution and then make full recursions on all the slice proof. Okay, so what does that mean? That means we split the whole execution of WebAssemblies. Let me show you, for example, sorry. Okay, I'll show you a very, I think, simple example about this is a WebAssembly code that actually has a front end written in Rust. It somehow does a very simple hash on about 3 megabytes bytecode. Right. Nothing special. I just compile that one into a WebAssembly. Okay, so after the compilation, you get this image.webassembly after we do WASM OPT, it somehow remove all the irrelevant runtimes from this image WebAssembly into output WebAssembly. And let's recap what WebAssembly looks like. It is something like this. So, sorry. Wasn't what? Sorry, I did not install the decoder of the WebAssembly, but the idea is that it has about 148 instructions, like that is the whole instruction set about WebAssembly. And and it's about 64-bit worldwide. So that means every operand you're handling with is 64-bit. And if we stick with this 64-bit setup for a while, and we're using KZG backend, which supports 252 bits, so that we can perform multiplication for 64 bits in 2 or 3 cells. And because we split them into different slices, we have to proving each slice proof to somehow actually make sure that the execution within single slice is correct. And this looks like this. let's prove this by run the WebAssembly, and the proving looks like this. So because now I'm using GPU versions that actually provides by Icicle. So this intermediate result that we have for each proof. And what it does is that it actually does the CI setup and then prove each slice. Because this one has about 360 million instructions, right? So it's split into 4 slices, right? And each slice will do a proof, and we'll see that we spend some time, about 4 to 5 seconds, on the commitment, and which is MSM, and then we see that the final proof time is about, for each slice, it's about 10 to 12, right? And we repeat that for 4 times. Okay. But after this, we did not actually get the whole proof of the execution because we only get the slices proofs. Okay. So yeah, there's a last slide which will actually, I'll quit that because we're not going to verify that. Okay. And this will give us all these small slice proofs underneath, right? And these are not connected. So that means when we to have these slice proofs, we have to make sure that the memory continues between different slices. And there are many ways to do that. We happen to choose a very old school technology, which is actually comparing the memory column, the commitment of the memory column. So that means for each proof in the batching, we make sure that the commitment of the memory column for the previous slice is equal to the pre-image of the next proof of the memory column. Okay, so, and because every time when you batch a proof, you need a universal prover that actually generates a recursion circuit, right, which is the verification algorithm that returns another circuit. And then this has to be generic. That means every time you cannot change the VK, otherwise you will get different proofs or VK setup for each row. To use that, we still happen to choose an old school version of this recursion circuit. It's a full recursion, so that we actually encoding the pairing algorithm into this circuit. So then every time we do a circuit. But there are drawbacks of this because every time you do a full recursion, you have to wait for the previous recursion to finish to actually finalize. But the good news is that although there are lots of benchmark externally says that KZG recursion is slow, but thanks to the unpairing algorithm optimization from Zaverucha labs, this now can be reduced to about 3 to 5 seconds. So that means we can somehow, in GPU, this talk I will actually elaborate a little bit about this recursion circuit as well. But the idea is that we use a full recursion and we do the recursion all the way through to the final proof and just try to give some feeling about how the recursion does. It is the recursion because this will actually uses the instance data that we generated before, and every time, so sorry, this is done in CPU. It should only be done once, but because I'm writing a CLI test script, this has been done many times. So what you know is that every route, it takes a few seconds, that's about 4 seconds, to do a recursion, and then you just repeat this process so that in the end you get a fully batched proof from beginning to end. And because for each round, you have to add in a recursion circuit proving here, so the total proving time is not only the proving time of the get circuit. It should be a sum of the whole proving time in one GPU. That is about if you're using open source, GPU is about 12 to 13 seconds plus 4 seconds. So it needs about 17 seconds to generate 1 million structures, but that's actually the benchmark contains recursion, right? So because there are lots of VM outside, they're only comparing about the proving time for the slices, but not mention about the recursion. But I'm going to actually clarify that actually recursion for KZG is not that bad. But to achieve that performance, that we need to do lots of work on how to pipeline the proof. Okay, so this talk, the main target of this talk is to try to explain how we can shrink the proving time to this stage and even further to about 10 seconds. But you will see that if we're using the background of the initial implementation in 2022, it is implemented in Halo 2, and it needs about 5 minutes, 5 full minutes in CPU to do this proof in one round. So that means we somehow reduce that to 17 seconds each round, comparing to initially 300 or 400 seconds in CPU. Okay, so why this is possible? And then the problem is that why, because if you look at some other proving benchmarks, you will see that usually the GPU optimization for Halo-based, maybe zkEVM, is about 5 to 6 times, right? So how to actually increase this speeds up from 5 to 6 times to 50 times, or 30 times to 50 times. 50 times on the guest circuit and 30 times on the recursion circuit. So how to achieve that? It's the main target of what I'm going to explain in this workshop. So before I explain, I'm going to just recap the structure of the Plonkish circuit. Okay, so because there are lots of protocols in KZG backend, right? Logup, lookup, shuffle, permutation, right? Okay, so I'm going to abstract the Plonkish circuit just with 3 abstractions. The first abstraction is the witness, because the whole circuit is basically a large matrix of witness. And actually, we will divide them further by the derivable witness or the polynomial calculated witness. And the second part is the relations between the cells. So it's basically permutations. And the third thing is the witness between columns, right? And we sometimes call these gates, call these permutations. Okay. And what we always do is, so now before I talking about the breakdown of the performance, we would like to study an example about a very simple logup argument. For example, I have A and B and as columns, and I would like to check A and B are within U16, right? And in logup, so sometimes we have to do this, right? And do a running sum of this. And you can consider that if I put that into the derived witness, right, then I have the committed witness. But if I do not actually put that line as an explicit witness, we have a degree increase in the final constraints, right? Either you put intermediate witness that is derivable, or you increase the polynomial degree of the final constraints. But there's one witness that you cannot derive from just putting that into the final evaluation, because this MI is not polynomial derivable. Okay, so that means we have to have an extra column. Sorry.
But what's the degree here? Like it looks like 2, no?
So what is degree here is that
of the constraint number 4.
You mean this one?
Yes.
Okay, so you cannot say this is equal to 1 because you have 1 over that. You sum that up. You do not want to put intermediate, which is here. You have to you have to multiply each, right, and sum them up. So if you combine two of them, then you actually multiply each one by this. The degree will be 2, right? So you have one more group, the degree goes up by 1, right? Depends on how many columns you have, right? But if you actually put this as an explicit witness column, then you do not have to put this down here. So that means you reduce degree by multiply the denominator. Am I clear?
Okay, so that maybe it's too much detail, but which quotient polynomial degree we want to achieve here? Like
So yeah. Oh, okay.
3 or 3?
4.
4. Like quotient will be 3.
So 4, yeah.
Okay.
So if that, so okay. So it actually can. So why we pick 4? There are some kind of theoretical behind that, based on the CPU performance of MSM and the GPU performance of H-poly. So we need to pick a ratio. So if we have some breakthrough on commitment, then we can increase degree on the polyeval. If we do not have the breakthrough, then 4 is currently our best trial. Okay. Okay. So now we know that the choice is that we balance between the columns, number of columns that we have to commit and the degree of the polynomial. There's something else, but basically we split them into. I just suppose that everyone knows this, and I suppose that we can have a formula on the final benchmark. Somehow the number of commitment that we have, right, for each column. So every time you increase intermediate derivable witness, you plus 1 on the number of columns, right? Because the commitment term for each column is somehow very stable. And then this is the term of the NTT part. And because you have to do on the extended field, the real term that is spent is this. Because if you have degree 4, then you plus 2 more degree, 2 times 2 on calculating the vector, the NTT vectors. And this is the open term that you're going to spend. But if we look at the final proof of the if we're spreading the final proof benchmark on 1 million instructions on the zkWASM, you will see that it's on GPU it's basically 5.5 seconds on poly evaluation on degree 4, right? And you have a few that's about 200 columns that you have to commit before you're doing poly evaluation, and you have multi-opens about 700 milliseconds, right? So it's about 5 seconds, and about less than 1 second. Okay, but this is not the case on CPU. So this is the benchmark breakdown on how it used to be on CPU. So in CPU, poly evaluation takes about 300 seconds, and commitment is about 50 seconds. Okay, so that actually gives a problem about, so you cannot make a circuit that actually is fast in CPU and fast as well as in GPU, because in CPU, what we would like to do is that we somehow would like to reduce the polynomial degree and then push everything as intermediate columns on that. Let's just skip this, because these are also derived or non-derivable witness. Okay, so in CPU, what you would like to do is that you would have every polynomial derivable witness as a separate column, right? So that you can downgrade the degree of the poly evaluation and then move that into the columns, explicit columns, and then commit that. Okay, but in GPU, what you're trying to do is that GPU, what we're trying to do is that instead of actually delegate all computations to MSM, we would like to make the polynomial very complex as possible so that there is no intermediate witness can be put into the witness matrix. So that means when we actually pick protocols, we would like to pick protocols that has polynomial derivable witnesses, right? So for example, everyone tells that, okay, maybe lookup is the best, right? But lookup has a problem that MI is not polynomial derivable, right? So every time you have a non-polynomial derivable witness, you have to put extra and you're adding that to the commitment. So when we actually choose the combination about protocols, we need to make sure that if this can be moved to the polyeval without adding new commitments, we should do that. Okay. But only moving this into the poly evaluation does not actually give us 30 or 40 times of speeds, because you see that the NTT now takes about 9 milliseconds, while this is only about 15 times quicker, right? This only takes about 15 times quicker. So there needs to be some fairly breakdown of the micro benchmarks to actually somehow make this faster. And we noticed that, so now doing micro benchmark. So there's some little secret on writing CUDA optimizations. So the first thing that in the CUDA, we have the caches and the cache miss and the time cost of each operation, right? So, sorry, this is for the last thing, okay. So now, if we look into these three different expressions, the very common guess will be these two should be the same computation time, while this should have extra computation time, right? That's the common sense, because that's how lots of people doing NTT or optimizing NTT4, they think every time they have one stuff or one vector here, it has to be the NTT of the initial vectors. Okay. But if you benchmark enough kernels, you will find that it's completely not the case. You will find that these two have exactly the same amount of time, maybe 1 or 2 milliseconds difference. But these two, this is, sorry, I should put this to be a D here, B here. So you put B here, then this will be the same. And so the current situation that these two are the same, and this is slower than this. And the reason that this one is slower than this is because it actually touches memory miss here for the vector of E. Okay. So now this gives the idea of put as many relevant vectors in one kernel as possible. And how to do that? So that you have to make sure that your GPU memory can hold all the memory miss or cache all the vectors in one place. But it's impossible, because every vector you have on K22 is about 128 megabytes, and the GPU only have 20 gigabytes. You can only cache about 60. So that means you have to choose what vectors you are going to cache, so that every time you put a very super complicated valuation here, you get the constant time of valuation. And this is, okay. So, and this has a limit, because once you put lots of vectors here and lots of here, at a certain stage, the GPU somehow hit its boundary, so the time starts to increase. Okay, so to do this, what we do is that we have to very carefully measure how much vectors we can cache on GPU, right? Because if we would like to calculate this, then we will have to cache 1, 2, 3, 4, 5, 6, and plus 2 intermediate vectors to actually holding the intermediate values, right? You have to take it very carefully about the intermediate values. So to minimize intermediate vectors that the GPU would like to cache, we have to always put a tree so that the right-hand side only have length 2. That means you only need to actually have 2 vector caches. Okay, so now we have to move this to the, so we have to swap the left-hand side with the right-hand side. And this actually makes huge difference if you do swap, right? Because by swapping that, you have 1 more cache, then you can add in more expressions here, and you can have smaller number of groups when doing the evaluation. So we have 1,300 terms of degree 2 or 4 in the poly evaluation, and if we can somehow fit that into maybe 1 group, then it's a very small constant term. But after we're doing this, we still have to fill in that into about 20 groups. Okay, so, okay, and you can do that manually when you're coding that, or you can do it automatically generate CUDA kernels, right? But that's details. Okay. Okay, so if we do that, it is still not enough, because if we do some calculation on the numbers, if we already know this observation, then we still have 2 choices. So one is that we do the NTT, all the vector entities before, and every time we hit a miss, we're loading them back into the GPU. And this cost me about 20 milliseconds to do a memory transfer, right? And because we have a few groups, for example, in our cases, we have about 25 groups. And you're doing this copy, it will take you about close to 8 seconds, right? If you're comparing to my previous command line, the whole point only takes about 2.5 seconds. That means, just like CPU, if we just like CPU doing the NTT for all the vectors and loading them on demand, it doesn't work. It didn't work because the memory copy, the bandwidth will be the bottleneck of this solution. And never to say that we still have the pre-calculation, which is 1.8 here, right? So if you're doing the traditional way, you have at least 10 seconds to do a poly evaluation for just the gate expressions, right? If you look at the number here, the gates should only take 2.3 seconds. So that's the one. And there are some other gates that you cannot actually put into the gates, large gates polynomial. Okay, so how to somehow reduce this into what we have now is the second approach. The idea is very simple. We never do NTT before we do the calculation. Every time we're in the GPU, we find that we have to do a degree 4 NTT. We're doing that in GPU in a synchronized way, right? Because there are calculation latency, and we still have some extra GPU resource. So we do use the leftover GPU resource to do the NTT, and this only costs about 9 milliseconds doing the NTT internally in the GPU. So this solution has a problem is that every time we have missing a hit missing on the vectors, we have to spend 9 milliseconds to do the NTT, right? But the gain is that compared to 20 seconds, we save 11 seconds here when we hit a missing. And the majority of this, the majority earning of this is that we can cache more vectors because the non-entity, the vectors not in the coset form, right, is 4 times slower than the degree for coset, extended field vectors. So that means we have 4 times more space to cache vectors in GPU, makes the group's number shrink by 4, right? And then you get this, which is exactly we get 2.5 seconds doing this. And by repeating this, so that's the polyvaluation. By repeating this, we can do that for lookup and permutations, right? If you can somehow shrink the number of permutations by rotation, you get a little bit more earning. But this somehow makes the 300 seconds in CPU into about 5 seconds in GPU. Okay, that's the optimization for the polyvaluation. There's another optimization that we can do is at the beginning we say that when doing commitment, this time cannot be saved because initially we need to do this GPU is using, I think, the fairly fast ICO library. So, but there's one more trick that you can save the time of this state-of-art benchmark by just writing a GPU library for 64-bit MSM, because when you're actually making a virtual machine that all the witness is about 64, most of the witness is 64. So by implementing special MSM, because we are not experts on implementing MSMs, we design a very legacy method to actually implementing 64-bit MSM, but it's still quicker than the state-of-art 252-bit MSM, and it saves GPU memory as well. So by doing this, we get another about 10% or 15%. Okay, so that's for the get circuit. And now for the aggregator, for the recursion. So because recursion is a large chunk of MSM circuits plus Parry circuits, and the recursion uses CRT to actually simulate the field, which means the 64-bit MSM does not work in recursion, right? So you have, in the recursion, the only thing that we can apply is the polyvaluation optimization. Okay, and this is the benchmark after you doing recursion optimization. You see that we still get 30 times improve in the polyvaluation, but not that much on MSM. Okay, and there's one small little thing that actually makes recursion slow, because every time you generate witnesses for the recursion circuits, you have to do witness generation for MSMs. And this cost me, because now I'm trying to move everything to GPU, this cost me about 2 seconds in a legacy CPU, a desktop i7 something. If you switch to a powerful CPU, this could be improved, but the whole point of this work is somehow we can delegate more stuff into GPU and have a very cheap CPU. So this will cost about 2 seconds. Okay, currently I have no idea how to improve doing a synthesize in GPU, but you will see that this actually occupies 40% comparing to the GPU calculation in the recursion. Okay. And there's other thing that you can somehow reduce the damage that recursion caused on the prover is because if we remember the big picture that every time we do a recursion, we're doing a batching on the previous proof, right? If the recursion circuit is nice enough, theoretically we can hold 2 guess circuits, right? Every 2 circuit slices, we do a recursion. That will actually reduce the damage of the recursion by a factor of 2, but we did not do that because we would like to have something called host precompiled circuits. So yes, we can remove this out. and plug in another guess here. But in our solutions, we actually plug in a host precompiled here. Okay, so now, why we need to do that? It's because sometimes there are circuits like signatures, ECDSAs that we need. It's very laxy when you return that into WebAssembly code. Even WebAssembly is 64-bit, but it's still slow. Okay, so the idea of encoding host APIs into WebAssembly is that we define the host API here without actually enforce any constraints on that. And this will actually compile to, now we have WAVT to show the compiling result, so we have this. And in the guest circuit, when we actually have host operations, we just fill in all the witnesses here. And without proving anything about the constraint of the witness. And we have another host circuit that actually enforce the input and output by the semantics of host operation. And in the batch, there's something underneath out of the screen. In the batch circuit actually comparing the column of this, the commitment of the column of this, with the commitment of the column on the host circuits, so that they can just connect it. If you like, you can write in the host circuits using GKR and using zero morph to somehow comparing the multi-write commitment with univariate commitment. So that gives me a little bit flexibility, but at the cost of we can only doing recursion for one slice proof, right? Because we're doing some, if we're actually adding host proofs here, we don't have enough rows in the recursion circuit. Okay, if anyone interested in connecting GKR with KZG, then there's a doc here, but that's not the current target. Okay, now we have the speed optimization, right? So this gives me about 16 to 17 seconds for 1 million instructions. And it seems that I have touched the boundary. I cannot do even further. But what we can do is that I can shrink the trace. I mean, so the story is that most of the CKVM somehow choose to use a 62-bit simple instruction set because you do not need to handle lots of gates, which actually improve the speed. But the problem is that you just imagine that you have a U122 arithmetic in DeFi system that it usually takes about more than 50 instructions to do a U128 in DeFi, right? And in WebAssembly, it's still taking about 30 to 40 instructions. But that's a saving of half, right? But actually, we can save that by removing stuff like stack operation. Just imagine that in a register-based VM, right? Every time you have to do an operation, you load something from memory and put that into the register, and you do the operation and then store it back. If the register actually stores the intermediate result, then you do not. You can save that store, right? You can save that store. But in the stack, but because register still is part, you still have to actually store the register back when doing functions called context switches, right? So in the stack-based VM, what we can do is that if we're looking at this trace, we will find that there are complicated instructions like this, or you can replace this by I64, any complicated instructions here. So you can replace any complicated instructions in this graph with this I add. And you will find that there are two wasted instructions at this point and this point. These 2 points are just specify the stack pointers that your instruction has to apply, right? But that's actually a WebAssembly feature. So you specify the stack position and load that onto the top of stack, and then you do the operation. So if we would like to actually simplify the trace, we can remove these two instructions into the circuit of the add. That will actually save you, in this case, about 60% of the instructions. And in overall programming, usually it saves about 45% of the trace of the WebAssembly. Okay, so, and this only increased a little bit about the poly evaluation part, right? It has nothing to do with the commitment part because the columns, number of columns fixed, right? So by actually letting emit this and move that into these instructions, our measurement that only gets 3% performance penalty, but you get super smaller trace, right? You can have a try and turn the zkWASM flag trace optimization on for implementing a curve in WebAssembly. You'll find that it saves about 40% of the trace. And if you're comparing that one with maybe 32-bit, it saves more. Especially, it saves memory copy. If you're writing lots of Rust code, there are lots of memory copy, and it saves memory copy, bitwise stuff, and saves this stack. But if you're comparing to register-based VM, then this will be register loading and store. But actually, in a register-based VM, they do not get as much damage as WebAssembly because some of the intermediate result can stay in the register without storing back. But in WebAssembly, this is the fact. Okay. So yeah, that's basically what I'm trying to talk today. And at the end, I would like to quote hardware outlooking that can be done to further improving a VM. And this is something that I read from Dent's FPGA benchmark. But let's keep it simple. We can get polynomial back to less than 2 seconds if we have ASIC in about, not that maybe 28 million. So we will do this, we get about 2 seconds poly evaluation. But the problem is that once you touch that boundary, you only get 3 seconds improvements. Right? It's not big deal to actually make ASIC at the moment. But actually the ASIC can improve the poly evaluation by another factor of 50, more than 50%. Okay, thanks. That's my talk. If you have any questions, you can ask. Yeah.
What's the benchmark results using FPGAs? Where does it come from? And these are the same benchmark?
The same benchmark. You just replace that with FPGA.
Okay.
Yeah, so they have an FPGA library. So
but how do you know it's the same? Because you run this on some input you generate, no?
Sorry?
What's the input for this benchmark? How do you know it's the same input for
they run this benchmark on their FPGA machine. So we have cooperation with them to test that out. Yeah. But this is an estimation, so there are some. This is the benchmark test here. So that's the thing that they tested. And they presumably, if you do ASIC, you get increasing heads and something else. I think we can publish this. They sent that to me with no any secret, so we can have a look at this. But the problem is that if we do an ASIC to just increase 3 seconds, maybe it's not worth that. You have to, maybe if you can add in MSM to the FPGA, then you get huge M. But currently, 64-bit special MSM works fine. Because I think every time you get a 64-bit CKVM runs in 10 seconds or 15 seconds, at the moment should be fine for most of the scenarios. But I mean, the potential is still there. You will have powerful hardware designed for BN256 poly evaluation.
I have a couple questions.
Okay, no.
Well, first off, the Jan's idea about using the multi-set hash for improving the memory integrity.
Yeah.
Using generative. Do you think
That's
significantly improved performance here?
That's so because we have a simpler model because the multi-hash is using a hash that you can commute, right? Okay. So what we do is that we very close because we not actually doing hash. We're comparing the commitment. Yeah. So we gain a little bit if you're doing multi-set hash, but because we have to compute the commitment doing the proof generation, right? Anyway, so this is a byproduct in our use case. But the shortage of our solution is that because we have 2 columns of the memory, that's k equal to 22, so that's only 64 megabyte memory. You cannot make bigger memory because we're using commitment polynomials. So we compare the commitment between the slices to actually ensure the memory are continuous. This saves the hash, but introduce a memory boundary. Yep.
Just a generic question for you.
Yeah.
One of the powers of WASM is that we can use these on mobile devices, which have very different architecture for the GPU processing.
Yeah.
And that there's not going to be much penalties from memory for swapping out the different caches because of
So to be honest, I did not see any customers using that in.
Okay.
So people using that just because they have a browser application written in TypeScript, they port into assembly script. So if people using Rust, they maybe intend to using there are lots of very fancy VM there like RISC-0, SP1, right? But if people not bothering writing Rust, then WebAssembly in a browser will be a choice. Right? But if you're doing a DeFi, because we providing solutions for some DeFi systems. If you're doing DeFi, then you get quite a few benefits by having 64-bit and shrink the trace. So U128 DeFi arithmetic is a trace killer for 32-bit.
I don't know what to call this, but reducing risk in making it changing the opcodes from including the trace information.
Yeah.
Is there, have you found a trade-off
Yeah.
between reducing your trace in instructions, between that and also introducing more opcodes?
Sure. So there's a. So you're looking at the breakdown of the benchmark. Okay. So because I'm doing a VM, right? All the stacks, registers, memories, everything that you have, even you have smaller set of instruction, you cannot shrink the columns that you have to commitment a lot, right? So in a GPU, not like CPU. In CPU, you get lots of gain by using simple instructions. In GPU, if we shrink our instruction set from 140 to maybe like RISC-V, like 30 or 40, right? You get maybe 50%. So you get that shrink by 3 seconds. 3 seconds out of 12 is not very attractive to us because you're giving, so there are some instructions that cannot be very easily implemented in 32-bit. For example, U64 signed reminder, right? But ironically, this instruction is not used for applications very often. But 2.7 seconds in GPU is, I think it's fine. it gives fully competitive with WebAssembly in browser.
I also just have one last generic question about,
Yeah.
like you said, the lab circuits are getting to the point of metal at this point, so you
Yeah.
can't optimize them that much.
Yeah.
So, but at the same time, the recursive proof,
Yeah.
do you see more work being done to optimize those in the future?
So you're asking whether there will be further optimization on the recursion side. I hope so, because I think some other VMs can do recursion in GPU in 1 second. I totally admire how they achieve that. We have 3.5 seconds plus some synthesizer cost. I think, because this is KZG proof, right? If we can somehow using fancy folding to actually doing the recursion, maybe we get some improvement. But because we are small group, I cannot afford to actually dive into other recursion at the moment. But I hope maybe after a while we get some better MSM synthesized to actually wipe out 2 seconds on the synthesizer. Yeah.
Oh, on that too, secondary thing, you mentioned that in the synthesis it's actually performs better in your CPU.
Yeah.
So yeah, you see that.
So
you see the GPU case being.
I want to have, because we have a proving thing in cloud, we would like to actually shrink the amount of CPU usage as much as possible so that I can, using 1 CPU, not that good, not EPYC CPU, but a simple CPU to actually have 8 GPUs. So, but if we focus on doing that, the synthesizing of the recursion will be 2 seconds at the moment. It depends on how much I can afford to pay to increase the CPU standard. I think these days, if you get CPU EPYC 9 something, it is twice or maybe 1.5 more expensive than GPU. So yeah. So if you can tolerate the 2 seconds of synthesize, then it's fine. Not many applications are very strict on the final batching speed. But yes, I know some VM has recursion for each slice that can be diluted into 1 second. That will be a huge benefit for them to have that. But our bottleneck, I find at the moment, is the recursion. Right? Even you somehow shrink the traces, improve the speed of guests, that only gives you 10 to 20. But recursion will be a majority target that I should focus. Yeah. Okay, thanks. Thanks for coming.
Thank you.